Hi everyone. In this video we're going to learn more about geometric sequences. So let's recap what a geometric sequence is, and then we can jump into the objectives of writing explicit formulas and figuring out all the important information. A geometric sequence is a list of numbers where each term is found by multiplying the previous term by a constant number. Okay, let's write that down. Get your own definition. If you don't like mine, that's totally fine. Or you can just write down what I'm writing down. Each term is found by keyword multiplying, underline that a few times, previous term by a constant. I can't spell previous merely. Previous. And another keyword is that constant word there. Okay, because you have to multiply the previous term by the same number you multiplied the previous term by. Now that constant number is what we call the common ratio. So more specifically, the common ratio is the factor between any two terms. Or I should say the multiplied factor. The multiplied, you see what I did there? That was going to be an F, but now it's an F. Anyways, the multiplied factor between any two terms. And we often call the common ratio R is the variable. R for ratio. Now that we got that out of the way, let's look at some examples, shall we? So we're going to start with example 1A. So let's figure out what the relationship is between these numbers, then we'll go ahead and write the explicit rule. So pause the video and figure out the relationship. I'll come back with the answer. Since we're studying geometric sequences, this shouldn't have been too tricky. You realize that each one is multiplied by 4. I just want to make sure you're practicing looking at patterns. Okay, the question becomes, how do I write an explicit rule for this? So you can kind of do what we did in class and compare this to a function, where n are your inputs and an are your outputs. So this is term 1, 2, 3, 4, which is kind of like your x values, right? And term 1 produces a number 5, 2 is 20, 80, 320, and figure out the relationship between those. You can even graph it if you want. Since we're only doing 1, 2, 3, 4, I'll just look at a positive axis here. So 1, then you have 5, 2, you have 20, 3, you have 80, 4, you have 320, and you're seeing that it's growing at a rapid rate, or it's growing by an increasing multiplied factor, which means that this is going to kind of model what we call an exponential function, although this is not a function, but you can kind of visualize it that way. Or you can think about it, you're multiplying by an increasing amount of 4s, right? So from 5 to 20, I multiply by 1 4. From 5 to 80, I have to multiply by 2 4s, or 16. So that also hints that it's similar to exponential. Now to formalize this, the general formula for any geometric sequence is the formula any term equals the first term times the common ratio raised to the n minus 1 power. Okay, this is the general formula you can use for any geometric sequence. So to kind of plug in those numbers and just confirm that this works, the first term in this case is 5. Our R, right, is our common ratio, which is 4, raised to the n minus 1. And you can check that to see if it works for here. So if I plug in 1, will I get 5? So it'd be 5 to the 4, 5 times 4 to the 1 minus 1, which is 0, which is 5 times 1, which works. Okay, so that's just a really quick, easy way to get the formula by, memorizing this formula. But I don't want you to memorize. I want you to understand where these come from and be able to derive. I'm going to give you 2 different ways to understand this. Okay, one, you can compare it to an exponential function and say, okay, I know that I'm multiplying by an increasing amount of 4s. So that means 4 has to be the base of my exponent. And we might initially think it's 4 to the n. Okay, if it was 4 to the n, then that would be the sequence 4. 4 times 4 is 16. 4 times 4 times 4 is 64. But that's totally not the sequence I'm modeling here. And all of these are factors of 5, right? 5, 20, 80, 320. They're all divisible by 5. So that kind of hints to me that this would need to be multiplied by 5. However, if this is my sequence as it is now, then it would, and I'll put the n out here, but if this were my sequence right now, I would have 5 times 4 to the n. So my first term would be 4 to the first time, and my first term would be 20. But really what I need to start with is 5. So I need to kind of like shift it back 1 position, because right now this formula has this as my term 1. So in order to shift it back 1 position, you can add minus 1 to the n, which makes sense then, because if I plug in 1, I'll have 4 to the 0, which will give me the 5 that I want, right? Because then this would be 5 times 1. So you can kind of just think through it that way, if you like. Okay, or you can rewrite the sequence in a little bit of a different way. So let me talk about that. So my first term is 5, right? So let's just say my first term is 5. My second term is 5 times the common difference, which is 4. My third term is 5 times 2 of the common difference, right? To get from 5 to 80, I'd have to multiply by 2 4s. So you can say that's 4 squared, you can say it's 16, whatever you want to say. So my next term would be 5 times 3 fourths, so that's 4 third. In this pattern, we continue 5 times 4 fours to get to 320, so on and so forth. Okay, so I've just kind of rewritten my sequence as I understand what it means to write a sequence. I multiply by 1 4. Then I multiply by another 4, so now I have 2 4s. Then another one, so now I have 3 4s. Okay. If you want to generalize this a little bit, each time you're multiplying the term by the first term, right? There's a 5 in all of these. But then you're multiplying by an increasing amount of 4s. Okay, but this one has 0 4s. So maybe I should even write that in. So this would be 4 to the 0. Okay, so if you kind of substitute in variables for this, well, they're all going to have a 5, they're all going to have a 4, but they're all going to have a different amount of 4s, and that's where this n minus 1 comes in. So you can kind of make sense of the formula that way, and you can always rewrite a sequence like this to derive the formula if you forget this. I think that's a really great strategy. I'll leave B for you to try on your own then as a follow-up problem. I'm also going to leave an example 2, because it's basically the same thing, except it wants you to find the formula and then find the 18th term. So you just plug in like 18 for n, right? You can do that on your own. Something that's a little bit different, it's kind of like a working backwards, I like to think about it, type problem. So it says the eighth term of a geometric sequence has a common ratio of 3, and that eighth term is 10,935. And it wants you to go backwards and find the first term in the formula. Okay, so this might be a situation where you might just want to say, okay, I know an is the first term times my ratio to the n minus 1 and plug in what I know. So eighth term, that's saying your position, so that's n, is geometric, which is where I got this formula. Common ratio is r, and this is A8. So let's plug in what we know. Okay, I actually don't know my first term, that's what we're trying to find. I know my common ratio is 3. Okay, and that's not enough information to solve right now because I have multiple variables. So I need to use the fact that this is the eighth term, and this is the value of the eighth term. So I know A8 is 10,935. Okay, you can use the fact that you know A8 to find A1. So let's call AN A8 and plug that in. So 10,935 equals my first term times my rate, which is 3, to the n minus 1. But if this is the eighth term, my n is 8. So I'll plug in 8 minus 1, and I can use this to solve for A1. So just to kind of clean that up, you can be doing this on your own while I go through this. I'd have 3 to the 7th. Ooh, what's 3 to the 7th? It cheated a little bit and I already had it plugged into my calculator. So you can plug that in on your own just to confirm that I'm correct. If I made a mistake, let me know, of course. I think that's 3 to the 7th. Now divide both sides and I can find, my brain thinks faster than my hand sometimes. But again, I can find my A1, right? So those would cancel out. A1 is whatever this division is here, which a little birdie told me would be 5. Okay, so you can use these formulas, these explicit formulas, to do different things. And I kind of just used the formula I gave you today. You could derive the explicit formula without using just like plug and chug, right? You can think through it like I did up here. That's such a good strategy. But for, efficiency, I just wrote down the formula that I know. I'm going to leave B for you. Kind of already did for you, but I'm also leaving an example 4 for you to try on your own so you can test yourself. If you have any questions, please come to class with them. Otherwise, have a good night.